the rubber industry research. In this session, we have a presentation on a novel approach to improve mechanical and the self-healing performance of rubber. This presentation will be given by Mr. Mithun Das. He is a senior research fellow at Rubber Technology Center in IIT Kharagpur, based in India. As many of you know, Rubber Technology Center at IIT Kharagpur is one of the prestigious institute, offers various master's degree, PhD program. At the same time, they conduct extensive research for the benefit of the rubber industry. So we are pleased to have Mr. Mithun Das to give a talk on his current research, which is focusing on the mechanical and self-healing performance of rubbers. Let's welcome Mr. Mithun Das with his presentation.
Hello everyone, I am Mithun Das, a senior research fellow of Rubber Technology Center, IIT Kharagpur, India. Today I am going to deliver my talk. My topic is that a novel approach to improve the mechanical and self-healing performance of rubber. And this work has been done under the supervision of Professor Kingston at the Rubber Technology Center, India. And this is the IIT Kharagpur. IIT Kharagpur established on 18 August 1961. And here the location of the IIT Kharagpur on the Google map. And our research group, the Professor Kingston research group, he mainly work on the TPV, TPU, green tie technology, same memory, polymer and alloy, polymer and elastomer, and polymer nanocomposites, and synthesis and polymer for their medical and self-healing application. And coming to the content, so I am going to cover such points, mainly the general introduction, followed by the rubber, self-healing, elastomer and their application, experimental, mainly raw materials, and the preparation of the self-healing elastomers, and in the result discussion section, cover the mechanical properties and healing performance, and finally the conclusion. Coming to the general introduction, so basically we have to know what is the rubber. Rubber is a material which contains both the viscous and elastic component, and mainly which has the weak intermolecular force of interaction with high molecular weight, and the rubber, which is can insoluble but can soil in the some particular solvent like benzene, toluene, PTF, etc. And rubber mainly classify based on the origin, natural and synthetic rubber, and based on the application, it is general and special purpose rubber, and based on the polarity, it's mainly polar and non-polar rubber. And here some various rubber products like shoe, tire, hose, etc. And coming to the general rubber processing step, at the first main step is that the first step is that raw material handling. After that, mixing, and then molding, and then curing, and then finished goods. And after that, after the service life. So after the service life, what we'll do? We'll do the waste rubber product throw in the landfill or in the occasion and in the ocean. And so here, this is the picture. We have seen that in the day by day and the year by year, the waste rubber product gradually gathered and resulting a huge environmental problem. So what we'll do and how to solve this problem? So nowadays, the many scientists or many researchers work on the green tie technology, and also to reduce some the waste rubber product. What we'll do? So we do the recycle vulcanized rubber, or we can do the devulcanization. So devulcanization means simply we can break down the sulfur-sulfur bond. If we break down the sulfur-sulfur bond, what happens? That means the combination of vulcanized rubber product can be used, recycled, and reprocessing. And these are different root of the waste rubber products. So the waste rubber product, what we'll do? We can do the devulcanization, and devulcanization mainly ultrasound, microbial degradation, supercritical carbon dioxide catalyst, and also the another thing is the reclamation. In the reclamation is mainly pyrolysis and mechanical grinding. In the second approach is that dynamic crossing. So if you crossing the rubber by the some dynamic crossing, so what happened that dynamic crossing rubber product can be recycled, reprocessing, and also self-healing approaches. And also some supramolecular approaches like various supramolecular interaction inside the rubber matrix, and then after that product has a huge application. And coming to the general self-healing materials. So self-healing materials mainly apply electronic skin, sensor coating, and also some 3D printing application like self-healing shoes, 3D toy, and also self-healing elastomer, self-healing rubber also can be used in so tire also. In the classification of the self-healing material mainly two types, autonomous and the non-autonomous. In case of autonomous system, there are some mechanism mainly encapsulation and microcapsule and also mechanochemical. And in case of non-autonomous system, mainly light, mechanical, chemical, and heat. And in case of heat, there are some so many mechanism, mainly the covalent bond, hydrogen bond, ionomers, and fluorine. And coming to the literature survey, so the mainly scientists or researchers have worked on the self-healing elastomers. So I have highlighted few of them. And the Darstell proposed the ionic modification of the rubber for the self-healing material, and also Rao et al. Proposed that the stretchable self-healing polymeric dielectric crossing through the metal-ligand coordination bond, and the Zhu et al. Proposed that the self-healing natural rubber which tailor mechanical property based on the ionic supramolecular hybrid network inside the rubber matrix. And coming to the objective, so my objective is that the modify the elastomer to improve the mechanical and self-healing purpose. So elastomer mainly modify in two ways. One is the chemical interaction, means covalent bond formation. In the chemical interaction, mainly do the disulfide reaction and disulfide bond formation inside the rubber matrix. And the second approach is that non-covalent supramolecular interaction. So here having so different mechanisms like host case interaction, hydrophobic interaction, ionic interaction, pi-pi stacking, and hydrogen bond formation. And also we have choose the metal-ligand coordination interaction. Why we have choose the metal-ligand interaction? Because of the metal-ligand coordination bond are the thermodynamically stable and also kinetically level at a wide range of temperature. And now, what are the material used for this work? We have used the carboxylate acrylate butane rubber, Crinax RX750 by Lanxess Germany, which contains the 7 percentage of carboxylic group, 27% of acrylate content, specific gravity 0.99, and the municipality is 47. And also we have used the 2,6-diaminopyridine DAP ligand, and also we have used cobalt nitrate hexahydrate, nickel nitrate hexahydrate, and the zinc nitrate hexahydrate, these three metal ions. And coming to the experimental section, in the experimental section, we have prepared the various metal-ligand modified rubber compounds. And this is the formulation. So according to the formulation, we have prepared all the rubber compound in a 2-round mixing mill in a internal mixer Hake. Mainly two steps we have prepared all the rubber compounds. So in the first step, we have taken experimental rubber and then added the DAP ligand at 130 degrees centigrade temperature for 30 minutes. After that, in the second step, we have added the various metal ions at 100 degrees centigrade for 10 minutes, and then the rubber composite are passed to a 2-round mill. After that, molded at 170 degrees centigrade temperature for 30 minutes, and then and finally the molded sheet are subjected for the various characterization. And coming to the reaction scheme of the metal-ligand modified elastomer. So this is the extended rubber which has the pseudo-volage group, and this is the DAP ligand. So after addition of DAP ligand at 130 degrees centigrade, after 30 minutes, so what happened? The amide linkage was formed between the NH2 group of the DAP ligand and the pseudo-volage group of the extended rubber. And after that, after the addition of various metal ion, so what happened? The metal-ligand coordination bond was formed inside the rubber matrix. And coming to the result and discussion part, first we have analysis the FTR analysis. So while in the FTR analysis, we can understand the chemical interaction and inside the rubber matrix. So this is the piston XMBR rubber. The piston XMBR rubber, the characteristic evolution peak is that the 1725 and the 1694 mainly the pseudo-volage group and the carbon and also the pseudo-volage stretching. and this is the pure dap ligand. And after that an addition of dap ligand, what happened? The metal ligand the amine linkage was formed, which is confirmed by the 1693 and the 1618. Mainly the amide band 1, the carbonyl stretching, and amide band 2, that is the chainage bending. So which means the amine linkage was successfully formed inside the rubber matrix. And after the addition of various metal ions, these 1693 and 1618 shifted to the 1678 and the 1655, mainly because of the formation of various metal-ligand covalent bond inside the rubber matrix. And same thing also happened in case of nickel system and in case of zinc system. And coming to the after the FT analysis, in the FT analysis we understand the formation of amine linkage and also the metal-ligand covalent bond inside the rubber matrix, and then we perform the mechanical properties. So without metal ion, only the dap modified compound, the tensile strength is very poor, 0.7. After addition of metal ion, so the mechanical property also increases. So in case of cobalt system, the tensile strength is 10.3. And in case of nickel system, the tensile strength is 8.6. In case of zinc system, the tensile strength is 4.3. And this is the stress strain plot of the various metal-ligand modified rubber compound. And after that, we have performed the DST analysis to understand the thermal behavior. So in case of piston exchange rubber, the glaciation temperature is minus 25.2, and after modify the dap ligand, the glaciation temperature also increases minus 23, and after addition of various metal ion, the metal ligand covalent bond was formed, and that's why the glaciation temperature also increases. So in case of cobalt, the glaciation temperature is minus 15.6. In case of nickel, the glaciation temperature is minus 14.7, and in case of zinc, the glaciation temperature is minus 18.6. Coming to the stress relaxation study. So stress relaxation study means what is the stress relaxation? Stress relaxation is the decay in stress with time at a constant deformation. And the stress relaxation study we can do by the RPA study. And the stress relaxation study from we can understand the physical behavior and the physical cost linking inside the rubber matrix. So and also we know that at the relaxation time, how will be the cost linking density. So in case of only dam modified compound, at the constant modulus, relaxation time is 0.043. In case of cobalt continuum compound, the relaxation time is 0.84. In case of nickel, the relaxation time is 0.128, and in case of zinc, the relaxation time is 0.048. So among of these three metal ions, zinc has the lowest relaxation time. That means zinc can form more weak and dynamic coordination bond compared to the cobalt and nickel. And in case of nickel, has the highest relaxation time, means the highest metal-ligand constituent density, which means nickel can form more strong and rigid metal-ligand constituent bond compared to the cobalt and nickel. And then we have performed the selfing experiment. So for the selfing experiment, we chose a Damben sample. So this is the original sample. Before cut the sample, after that, after cut the sample at the middle of the sample, then we just join the two pieces of sample, and then the sample placed in an oven at various temperature and time. And this is the heel sample. After that, this is the stress sample. That means the sample is completely healed. And then we have performed the self-healing, we have calculated self-healing efficiency based on the tensile strength of heel sample divided by the tensile strength of virgin sample multiplied by 100. And then we have calculated the self-healing efficiency of the various metal-ligand modified rubber compound at various temperatures. So we start from the room temperature to up to 80 degrees centigrade. So at the room temperature, the cobalt modified compound, the healing efficiency is 21%, and the nickel modified compound is 17%, and the zinc modified compound is the 55%. So that means that zinc can form more weak and dynamic coordination bond compared to the cobalt and nickel. As the temperature increases, the self-healing efficiency also increases gradually. At 80 degrees centigrade, after 24 hours, the cobalt modified compound, the healing efficiency is 88%, and the nickel modified compound is 56%, and the zinc modified compound, the healing efficiency is 100%. So which means zinc can form more weak and dynamic metal-ligand coordination bond compared to the cobalt and nickel. And after that also we have calculated the self-healing efficiency at constant temperature and various time. So here The temperature is fixed 80 degrees centigrade, and we have changed the time from 0.5 hours, 1 hour, 3 hours, and 6 hours, 12 hours, and 24 hours. So as the time also increases, we have seen that the healing efficiency also increases. So in case of this is the estimated dye plus cobalt system, and this is estimated dye plus nickel system, and this is estimated dye plus zinc system. So finally, estimated dye plus nickel system at 80 degrees centigrade after 24 hours, the healing efficiency is 56%. In case of cobalt system, the healing efficiency is 88%, and in case of nickel zinc system, the healing efficiency is 100%. So the zinc modified compound is completely healed at 80 degrees centigrade after 24 hours compared to the cobalt and nickel. And then we have understand the healing mechanism. So what we'll do this when we cut the sample, what happens? The dynamic metal coordination bond are separate from each other, and at 80 degrees centigrade after 24 hours, these dynamic metal coordination bond are rewinded and then heal the sample. And the sample was healed or not, which are understood by the optical microscope study and the AFM study. So this is the control sample, means without metal-ion. We have seen that the optical microscope study, which is not healed at 80 degrees centigrade after 24 hours, and this is nickel modified compound. The nickel, we have seen that, which is also not completely healed. And the cobalt modified compound, we have seen that is the before healing and this is the after healing, which is healed but not fully healed. And also the zinc modified compound, we have seen that 80 degrees centigrade after 24 hours in the optical microscope study, which is completely healed. And also further we have done the AFM study. The AFM study, we have only performed the zinc modified compound because zinc has the highest healing efficiency, almost 100%. That's why we have choose the AFM study of the zinc modified compound. We have seen that from the AFM study, the sample also completely healed at 80 degrees centigrade after 24 hours. And then we have performed the morphology analysis from the ACM study and the KM study. From the ACM study, scanning electron microscope study, we have seen that the only dye-modified compound, the dye ligand are the solid particle uniform dispersed through the rubber matrix, and this is the nickel modified compound. This is the estimated dye plus cobalt modified compound, and this is the estimated dye plus zinc modified compound. So we have seen that after addition of metal, the Metal-Ligand portion one form, and the solid particle are uniformly dispersed throughout the rubber matrix. And also similarly, also we have understand also same study, and also same from the same images. Also we have seen that the Metal-Ligand the Metal-Ligand modified compound and the solid particle uniformly dispersed and throughout the rubber matrix. So from the ACM, the same study, we understand that the uniform dispersion and the better coordination inside the rubber matrix, which improve the better mechanical properties and the healing efficiency. And coming to the conclusion and future work. So in conclusion, we the self-healing of XMBR rubber base on the dynamic non-covalent metal-ligand coordination bond, which is successfully prepared by the normal Vulcanized system, and the metal-ligand coordination complex formation, which is confirmed by the FT analysis, and the XMBR dye plus zinc sample has the highest healing efficiency, which is almost 100% compared to the cobalt and nickel, and the AFM and the optical microscopy shows that the zinc modified compound is completely healed compared to the cobalt and nickel. In the future work, to study the supramolecular costing network formation in other unsaturated elastomers such as styrene rubber, natural rubber, and polybutane rubber, and to study the dual ionic crossing into the various elastomers by use of different amino acids like lysine, tryptophan, and to improve the mechanical properties and the self-healing efficiency. And also to study the effect of counterant on the mechanical properties and self-healing application, and the graphene and Higgins ionic liquid modified elastomer to improve the self-healing efficiency and also as well as the mechanical properties. And this is the reference of my work. And so coming to the acknowledgement section, so I am extremely thankful to IIT Kharagpur for their financial support. I am thankful to my supervisor, Professor Kingston Noskar, for his continuous support and guide. And I am thankful to my friends, my family members, and also my lab mates. And I am deeply congratulated to our industry news hour Technobeats for giving me this opportunity. Thank you all.
Excellent presentation on the novel approach to improve mechanical and self-healing performance of the rubbers. You may invite Mr. Mithun to come on board. Mithun, please join us.
Yeah, yes. Am I audible?
Yes, you are. Can you open your webcam too, please?
Yeah.
Okay, super. Okay. Hello, Mithun. Thank you for joining this session. First of all, sincere thanks to your supervisor, Professor Kinsuk Naskar, who permitted you to make a presentation with my request. And I'm glad that you are part of this rubber industry research program today. How are you doing? Your research almost done at Rubber Technology Center? What's the status?
Yeah, almost. I have almost completed, and like coming next 2 to 3 months, I have committed to a thesis, and then I'm looking for postdoc.
Fantastic, fantastic. And I have a couple of questions for you, Mithun.
Yes.
You know, you have done this self-healing research related to self-healing rubbers. Based on your whatever the outcome of your research work, what do you see? How do you see the impact on the future of the rubber industry?
Yeah. So if we look based on the application of a self-healing elastomer in the day by day and in the year by year, also gradually increases. Mainly, if we look like automotive industry and some medical parts, and also nowadays 3D printing application, some self-healing tools, and also the self-healing tire also application of also tire also like mainly the title of the tire. And also some sports tools and also some sports tools like watch band, then also self-healing material also huge application nowadays.
Super. So there, I think you see a lot of changes, improvements in the self-healing rubbers. Yeah. So.
Yeah. And also. Yeah, and also the one thing, one of my work I have published that, and on that work I have shown that the commercial application of self-healing elastomers and the O-ring application that at ambient temperature which can heal and automatically almost heal. So we can also use the product in the O-ring application, some oil seal and like that.
Oh, okay, super. I have another question about this self-healing efficiency. What factors influence the self-healing efficiency?
Self-healing efficiency, main thing is that some temperature also. So the main thing is that if you increase the temperature, any material like is able to heal. Means into the temperature, what happens, the diffusion happens inside the material. So today the challenge is that if you as much as the room temperature is the self-healing capability. This is the challenge. So I have also like one of my work that I have published that the automatically self-healing at the room temperature. So main challenge is the room temperature healing efficiency, the room temperature capability of the healing of the material. So in the higher temperature, it can like 200 or 150. That temperature is the material, any of the material, the diffusion happens. But the room temperature, the healing is quite difficult. This is the challenges nowadays.
And your title is a novel approach. So what is a novelty?
Novelty means here the Metal-Ligand for interaction and dynamic supramolecular approaches. So this is the novelty, and so in this here I have done the various metal I have used. So among of these three metal and the zinc and shows the better healing efficiency, almost 100% healing efficiency. So this is the novelty in this work.
Super. So Mithun, thank you very much for joining this session today. I wish you the best and keep doing good work. Okay, we'll be in touch. I hope to invite you in future episodes of the Rubber Industry News Hour. Thank you very much.
Thank you, sir. Thank you.
Okay, that's the presentation on the novel approach to improve mechanical and self-healing performance of the rubbers. So if you're interested in this